Hi everyone and welcome to this tutorial on RSPt calculations. In this video I will show you how to plot the band structure. Let us immediately go to the terminal to the example number 6, where I copied our calculation for cobalt to iron aluminum, which is already converged. We get a magnetic moment of close to 5 Bohr magneton and very low FSQ value. Now we will plot the band structure. It is basically a plot of eigenvalues along certain path in the Brillouin zone. So what we have to do, we have to create this path. We go to the directory bz, where we store the key points. We can use a very useful tool called kpath for generating k-paths in the Brillouin zone. So to construct this file, we need to know the Brillouin vectors, and we can get it from kub.int. Here we are. So we can start creating the kpath.inp file, which is the input file for the kpath program. We need to specify the Brillouin vectors, and now we have to give the coordinates of the high symmetry k points to generate the path in between them. We can see that the Brillouin vectors are FCC. It's very easy to find the positions of the high symmetry points. For example, I use this website. On the right hand side you can see the plot of the first Brillouin zone for FCC lattice, as well as all the high symmetry k points. And in this table on the left you can see their coordinates. The program kpath requires these coordinates to be in the basis of reciprocal lattice vectors. Namely, L point has the coordinates 1/2, 1/2, 1/2, meaning that we take the first inverse lattice vector, the second and the third, and we sum them up with equal weights. As you can see, L point is indeed located in between all these three vectors. Here is the list of high symmetry points, and as you can see, if we specify them in this particular order, we get a pretty nice path in the Brillouin zone. So we go from gamma to L, from L to U, from U to X, and then to W and K point. So let us just take this list of key points and paste it directly into the kpath.inp file. And what we can also do is to specify the label for each key point. So this was gamma, this was L, this was U, X, W, and K. And that's it. That's all what the kpath needs to generate the kpath. So let's run this program. And you can see it created several files, and one of them is called spts.band. Let's have a look. It has the same format as the files containing the k meshes, but now instead we have a list of k points generated along this path. And we have 312 points in total. And here you can see we go from gamma to L to U, etc. In the log file, we also get quite useful information. So this is the summary of what the code did. We can also see how many points there are in between these high symmetry points. And finally, we get this very useful block, which can be immediately posted into green.inp file. So let's do it. We copy these lines. We go to one directory above, and we create green.inp file with these lines. What the code will do, when we run RSPt next time, it will print the band structure and also projected band structure on the correlated orbitals, which we still have to specify in the cluster block. We can plot the character of the bands and see how much the correlated orbitals contribute to every eigenstate at every k point. So we can project, for example, on cobalt these states and maybe on iron. So we specified two cluster blocks. So we have one state, and here we specify 0 because there is no u and j to be added. Type 1, L equal to 2, energy set 1, site 1, basis 0. We can copy these three lines, and for iron we only have to change the type. And finally, there is one more little detail which we have to remember. In RSPt, the Fermi level is not stored anywhere. It is calculated on each iteration. And now we will basically perform RSPt calculation with the new k-mesh, which in fact contains the path in a Brillouin zone. And therefore, it's not a representative set of k-points. It's not meaningful to calculate any observables with it. And the chemical potential will also be calculated on this set of k-points. And in order to prevent the code from using the wrongly calculated chemical potential, we have to specify it here in this file. And this is done in the mixing block. You can look it up in the manual. So it should be given here. Let's look up this number. So we can go to the out file of our last iteration. And we look for Fermi. And here it is. So now we can paste it into green.inp file. Like so. And now we go back to the BZ directory. And we change the name of this file so that we can use link spts program. And as you remember, it requires the files with such a name, and we just can give it some specific postfix like band. Now we can go up and link this k-mesh to RSPt. So that's it. Now we're set to go. We can just run one iteration of RSPt. And since I have 312 key points and I have 2 nodes available, I can use them entirely, because the number of key points is pretty large in this case. It's done. Let's have a look at the out file. Everything looks fine. We just see what we specified in the input file. Here we get the specific value of the chemical potential, and here are some default values for plotting. So the plot was done with 1000 points in energy. The range of energies was from -1 Rydberg to 1 Rydberg relative to Fermi level. So Fermi level is at 0. And finally we have a smearing. So let's plot the bands. What kind of files did we get? We have the band.data, which contains the band structure, and we also have projected pband files, the data, and the gnuplot script to print it. So let's print the non-projected band structure. So you can see there are a bunch of parameters. Everything was prepared by default. You can see the labels of the key points will already be specified. There are some ticks on the y-axis. So we can, for example, comment these lines and use specific set of ticks. It will print the band structure and also the logarithmic intensity of the bands. Maybe this we can comment out for the moment. and after that we will get band.pdf. We can run GNU plot. And let's plot it on the screen. And here it is. We can see the band structure. Indeed, it's plotted along the K path which we specified. And the energy range here is in between -1 Rydberg to +1 Rydberg. And the Fermi level is right here. Since we have a magnetic system, it's a little inconvenient since we have both spin up and spin down bands at the same time. So maybe it's also useful to plot them separately. We go to the file band.gpi. Here at the bottom, we can see that there are a couple of lines which we can just uncomment to plot the spin projected band structure. We uncomment these 3 lines to plot spin up projected bands. These 3 lines are for spin down states. So we will get 2 out files, band-up and band-down.eps. So we start from up, and in this line we will convert it to PDF, like so. We can do the same for spin down states. And here we will just remove the EPS files. Yeah, we can just save it and run GNU plot once again. Yeah, we got these 2 new files, band up and band down. So let's plot them. Here we are. Now this is a little more informative because we can really see how spin up and spin down bands cross Fermi level. In principle, that's it. What you have to remember is that you have to specify this Fermi level taken from the self-consistent calculation. You don't have to do it if you have the self-energy, because the format of SIG file is such that it stores the value of the chemical potential. That's it for the moment. See you next time, and until then, enjoy RSPt.